Hello students, next let us look at how the sensor system is selected for implementation for any robotic system. Whenever we choose any sensor for any application, we have to consider many things because the proper selection will determine the performance of the sensor or the performance of the system, the amount of money that you are spending behind the system. You do not want it to be too costly also. At the same time, you don't want to make it a very cheap system. You want it to run nicely. So you have to look at the economy of the things. Similarly, proper choosing will also decide how easy it is to use. And finally, the applicability of the sensor. For many different type of situations, we are having different type of sensors. So let us look at some of the sensor characteristics that we should look when we are going to select a particular sensor system. The first thing is accuracy. Accuracy is basically defined as, if suppose there is a value that you want to find out and that is 2.485. The original value is 2.485. If you are able to find out something that is 2.482, you will say that it is pretty accurate. But if you are using a sensor which is giving you a reading 2.471, then you will say that the accuracy is not that much. Even though you can say that it is accurate up to first decimal point. But still the accuracy relative to this value is poor. So accuracy is defined as how close the output of the sensor is to the expected value. How close the output of the sensor is to the expected value. The accuracy, generally we all want that the accuracy should be high. But when you go for high accuracy, what happens is that the cost of the sensor keeps on going up. So if you are satisfied with this much accuracy, you can go with the system. It's not a big issue. But if you go for higher accuracy, the price of the sensor will go up. The next selection criteria is reliability. That means how reliable the system is. Now suppose, as I take the previous example itself, suppose you want to calculate a value 2.485 and you are doing 100 readings. Out of the 100 readings, most of the readings are coming close to it, whereas let's say 7 readings are totally off. That means their value is coming something like 3.8 or 0.4 or let's say 1.2 or let's say 5.3. So these values are totally off. They are totally off. So if these values are coming, you will be saying that, oh, I cannot rely on this sensor. I cannot believe what the output of this sensor is. So generally you look at the reliability, which is calculated by how many times a system operates properly divided by how many times it tried. So within the industry itself, they will put to test and find out what is the reliability. So if suppose they decide that the reliability is decided by that, if you are having the original value as 2.485, it should give me something between the range of a value, let's say 2.3 and 2.5. Suppose 2.55, let's say. So we will say that, okay, I want the range, this is the range within which the reading should come, and this is the accuracy I am basically looking at. Then next is how reliable it is. So you look at how many times out of the 100 readings, how many times the reading is giving you this value, that means between these values, and how many of it times it is giving outside those values. So these are those outside values. Okay, so suppose 7 values are outside, then totally 93 was inside. So you will say that this is 93% reliable. This is 93% reliable. Generally we all want that the sensor should process a high reliability. Okay, why? Because it should not lead to the failure of the operation. It should not lead to the failure of the operation. Okay, so when you go for higher and higher reliability, then again the cost goes up. So whenever you are trying to buy a sensor, generally you should ask, like, what is the reliability of this sensor. That means you are asking how many times when what is the percentage of correctness that I will get. So that is a ratio. It's a ratio value. So generally it will not come in terms of percentage. It will come in terms of ratio, which is 93 by 100, or I can say 0.93. Okay, which actually means 93%. Okay, so that is what is reliability. Next is the sensitivity of the sensor. What do we mean by the sensitivity of the sensor? The sensitivity means how much the output of the sensor is sensitive to the. So suppose if the change in input is, suppose this is what the one reading is, another reading is this, and another reading is this, then the output of that sensor, the value should basically jump in large values. Now that means the sensitivity, I'm not talking about that amplification should be high. I'm saying that the output of the sensor should reflect even small changes. So if a very small change comes here, here it will reflect as a big change. Why? Because the sensor is more and more sensitive. And sometimes you might have seen certain devices wherein, suppose if you are having a device like this, which basically fluctuates, the pin basically fluctuates to show what is the value that is being measured. You can see that certain sensors are very sensitive. They move at the very slightest input, very slight input, they will have a change in the output. So mathematically it is calculated as the ratio of the change in output in response to change in the input. So based on how much the output changes, you can decide how much the sensitivity is. For example, suppose the temperature basically changes. Okay, the temperature basically changes in a system. The temperature basically changes from 0 to 100. From 0 to 100, and the output of the sensor is basically giving you in, let's say, some value. Presently it is 10.9. Now if a sensor has low sensitivity, suppose the original temperature is 10.9, you are having a pretty accurate system, it is giving the output 10.9. but suppose if the system is very sensitive, if the value changes, the original value changes from 10.9 to, let's say, 10.8, then here also it will show a change of 10.8. Okay, here also it will show a change of 10.8. But suppose it goes from 10.9 to 10.8, but here it is still showing 10.9. That means this small change it has not sensed. It has not sensed the small change of 0.1. It might be still giving 10.9. And then suppose it goes 10.7, and then it gives a change of, let's say, again 10.7. So you might be thinking that, okay, it missed 10.8. No, at some other point of time when it is at 10.8, it is giving a result of 10.8 itself. But At certain times it is missing those values. That means that small change it is not able to detect. So that is basically low sensitivity. Okay, some sensors are very low, some sensors have very low sensitivity, some sensors have very large sensitivity. Okay, some sensors have very large sensitivity. Even a small change you will be able to detect. For example, suppose if you are standing on a weighing machine. Now if you look at the weighing machine, there are two kinds of weighing machine. One is analog values, which will have basically a dial like this, wherein the kilograms will be shown here. Suppose it is 60 here, 65 here, and then this is the arrow mark. Okay, and this dial basically keeps on rotating this side, or it rotating back and forth. And there is another digital one. In the digital one, it is basically directly showing the weight as suppose 60.43, something like this. Then you might have seen that a digital one is having very small change. If you are, even if you are standing and you are moving a little bit, these values will change. Whereas here it does not change too much. Even if you are moving a little bit on the scale, on the weighing scale, the value doesn't change much. Whereas here, even a slight change here and there, the value drastically changes. So it means what? It means that this digital weighing machine has a very very good sensitivity. So generally you would want that the sensor should have very high sensitivity, but again, with respect to price, the sensitivity will increase. If you don't want a very high sensitive system, you can do away with it. Next is linearity. Linearity of the sensor. What do we mean by linearity of the sensor? Linearity of the sensor means it represents the relationship. It represents the relationship between the input variation and the output variation. Okay. For example, if you are going to take the count of your blood oxygen level. Okay. So suppose if originally your blood oxygen level is 94%, and suppose the meter is not very accurate, it is showing 92%. Then the original value, suppose is changed to 96, then here the value changes to 94%. Then it is changing to, let's say, 98%, and the value here got changed to 96%. So you can see that that difference of 2 is totally getting maintained every time. Okay. So every sensor has a range in which it is linear. Every sensor has a range in which it is linear. So it is, suppose, the original value. Okay, and this is the measured value. And generally when you draw the output of the system, you will say that it is linear within a particular range. So that means it is having a linear value within a particular range, and linear is very important because, as I said you, suppose if it is 94 at 92, and at 96 it is not 94 but it is showing 98, then here the difference is 2, but when it came here the difference became 4. So when you would draw that kind of a system, so suppose if the difference is 2, that means this was the original value. The next case, the value actually is now increasing. So if you would draw that graph, the graph would look like this. That means for here the difference is 2, for here the difference is 4. So it does not make a straight line, it actually takes a curved line, and that is happening with most of the sensor beyond a certain range. So beyond a certain range this will slightly curve. So you will take only that range where it is linear. So linearity represents the relationship between input and output variation. It means that the sensor with a linear output, that means change in input at any level within the range, will produce the same change in the output. Okay, that means whatever is the change will produce a particular change in the output. Another one more, there is change, the same kind of change will be produced output. Okay, that is basically linearity. And For any sensor, there is a linear range, and there is outside that it is non-linear. If you have a pulse oximeter that people are using for a COVID, you just look at the data sheet of that. A data manual might be there, a data sheet might be there. You take that, most of the oximeters, they are saying that the value is not linear below almost 73-74 percentage, or some cases even 79 percentage. That means if its value comes above 74 percentage, its value will be, somewhat you can say that its value will be correct. But if your reading is showing as 69 percentage of oxygen level, then you cannot rely that this is a correct measurement. Its value may be even low, or its value may be even high. You cannot say that. Why? Because the reading is outside the range. So within a particular range, every sensor is working perfectly. Outside that range, it is not working perfectly. In case of pulse oximeter, you can check. If you are having a pulse oximeter, a data sheet, its range will be from something 75 percentage to 100 percentage. It will give an accurate value. Beyond that, it will be wrong. That is why where you might have heard about news wherein people were brought to hospitals. They said that his count was, when we took it first time, his count was 60 percentage. Within 5 minutes, his oxygen value dipped to 40 percentage. So things like this happen because when you are using a digital pulse oximeter, the range in which it is linearly working, that range is a very small range. Beyond that, the value can be anything. It can be correct, it can be wrong. Generally, when you have, or when you want a sensor which has a higher range of linearity, obviously you will have to design a system which is more and more perfect within a particular range. So naturally the cost will go high. So if you are looking for a pulse oximeter which gives you a range of accuracy between, let's say, 40 percentage to 100 percentage, obviously the cost of that pulse oximeter will go high. You might have already felt that why there is so much price change. Well, the price change in all these instruments happens because of the accuracy, the linearity, the sensitivity, all these things that we have studied here, they basically decide. Okay, next is the range. Next is the range. Range is referring to the maximum and minimum value that the sensor can sense, or you can say the minimum and the maximum value of the linear reading. For example, if you look at a weighing machine that is used for measuring the human body, it might be having a weight of, let's say, from 0 kilogram, or sometimes let's say 10 kilogram, okay, let's say 0 kilogram, all the way up to something close to 180 kilograms. Okay, now why is it that they are building it for this much range? Obviously a human can weigh, sometimes in very rare cases, beyond 180 kilograms, but most of the people, almost 99% of the people, or 99.99% of the people will fall within this range. So they need to make a sensor which actually measures within this much value. There is no need to go beyond this value, and that is what is referred to as the range of the sensor. Beyond that, if it goes, you cannot say whether this value will be correct or not, or it will not show any value because its maximum range is 180 kilograms. Or take the case of your bike or your automobile, wherein the range goes from, let's say, 0 to 220 kilometers per second, suppose. No, not per second, sorry, per hour. Okay, so this is the speed range. Suppose you are going at 220. Okay, suppose you are driving at 220, and suddenly you were riding in a flat road, but suddenly there is a slope, and that slope is such that the weight of the bike itself is pushing it at a slightly higher speed. So let's say now, because of the slope, the bike has gained 230 km/h speed, but the maximum range that it is able to show is only from 0 to 220. Beyond that, what will happen? Will the needle go? No, the needle will stay at 220 only. It will not go beyond that. Why? Because the range, the maximum range of the sensor is 220. It cannot measure a range beyond 220. That does not mean that the vehicle cannot go beyond 220. It can go at any speed. Okay, it can go at any speed. Okay. Resolution, the next criteria that is used for selecting an sensor system. Resolution is, basically speaking, suppose if you are trying to measure something, or let me say that you are trying to measure a temperature of some body whose temperature is, let's say, 10.45678. So this is the temperature, degree Celsius, suppose. Okay, and you are using a temperature sensor, basically a thermometer kind of thing, which is giving you a reading of 10.46, or let's say 457, or let's say 8. Okay, degree Celsius. Another one is giving you a range of, let's say, 10.4 degrees Celsius. Okay, so this is the original value, and if you would go, this particular number will go on up to infinity. 873241867328 like that. It can go up to infinity, because the exact value of temperature, the more there is the more decimal values you will put, that much value more accuracy it is happening. So which reading is more accurate? This reading is more accurate, or this reading is more accurate? See, as far as accuracy is concerned, you can only say that here it is 10.4, here it is 10.4. the accuracy is almost the same. But now what is the difference between these two is that the resolution has changed. That means it is giving you more smaller values, least count. It is giving you more least count or more smaller values of the original temperature that you want to measure. Okay, and these small values will depend on what is called as the resolution. So you might have seen that certain weighing device will give your weight as 60.3. Some will give your weight as 60.342. So what does it mean? It means that this is more accurate? No. The accuracy is almost same. But here the resolution is more, because it is giving you more smaller values. Suppose if you want to measure the resistance using a rheostat, we know that a rheostat is basically, you have all studied, it's a winding, and there is a pointer, and that pointer, when it moves from here to here, it measures one winding, isn't it? So what is the minimum, smallest, least count that it can measure? The least count that it can measure is basically the resistance of one turn of the wire. If you take a scale, a scale, so it is a 15 centimeter scale, then it is having from 0 to all the way up to 15. What is the minimum distance that you can the minimum distance you can go for calculating? That minimum distance is 1 millimeter. Beyond that you cannot go using a scale. Whereas if you would go for using a vernier caliper may have a least count of 0.01 millimeter. How? That is a different matter, but this is the least count that it will have. Okay, so that is basically what is resolution. In the case of a digital device with n bits, the resolution will be full range divided by 2 raised to power n. That means, suppose if you are having a temperature reading which is basically going from, you can measure from 0 to 200. Okay, so what is the range? The range is 200. The range is 200. And suppose the digital device you are using, it may be an 8-bit device or it may be a 16-bit device. Now if it's a 8-bit device, what is the least count that it can show? The least count it can show is from 000000000 up to 000000001. Okay, so that one step is basically given by that. And how do you find that smaller step? You basically take, since it's an 8-bit, you take it as 2 raised to power 8. So the resolution will be given by that, the total range, the full range divided by 2 raised to power 8. So this is how much? 200 divided by 128. So 200 divided by 128, you can see, what is the accuracy, not accuracy, sorry, resolution. That means the minimum one step can be represented by how much? You can see that. Okay, so 200 divided by 128 will be 1.56 degrees. That means the minimum resolution that it will have is 1.5. The least count that it can have is 1.56 degrees. That means, suppose now it is going to measure 10 degrees Celsius. Suppose the next value that it can measure is 11.56 degrees Celsius. That much small is the least count. Between this, it cannot measure a value. Okay, whereas if you are going for a 16-bit, when you are going for a 16-bit, the value is totally different. Sorry, 2 raised to power 8 is 256. Sorry, so it's not to 128, it's, let's say, 256. So the value is now going to be 0.78. So the minimum count is 0.78. Just like this scale can measure a minimum of 1 mm. Just like that, this one can measure this particular device, which is having an 8-bit digital level. It can measure something which is having a difference of 0.78. Whereas when you go for a 16-bit, in that case it is going to be 200 divided by 2 raised to power 16, which is 65,536, something like that. And in that case, you can see that the resolution is very, very high. That means it will come as 0.003. That means it can measure a value as small as 0.003. So that is how the resolution in a digital device changes with respect to the number of bits. Next, we look at the response time. What is response time? Response time is the time that a sensor output requires to reach a certain percentage of the total change. That means how fast it is able to change. That is the response time. For example, you are measuring a temperature change and the temperature goes from 10.95 to, let's say, 11.32 within a very short time of, let's say, 0.5 seconds. 0.5 seconds. Okay, and in another 0.5 seconds it changes from 11.32 to, say, 10.84. Okay, so the output is changing very fast. Now when you are trying to measure this, suppose the response time of the sensor is very small, then and suppose it is very accurate one. Okay, it's a very accurate one. Suppose it measures 10.9. The accuracy is good, but suppose the resolution is small. So 10.9 it is giving a reading. Whereas this reading is coming after reading, after the sensor senses 10.95, it gives a reading of 0.9. It should give a reading of 0.9. But this takes, suppose, 1 second to change. It suppose take 1 second to change. Whereas the original value has now gone from 10.95, it has gone to 11.32, and then it has become 10.84. Okay, and in that case, if the response time is not very small, if the response time is not very small, it will basically miss this reading, and the next reading that it will show is basically going to be this. Okay, the basic next reading it is going to show is this. So it will jump these values in between values. So if the response time is very fast, then the sensor will be able to track the output very quickly. You might have seen in the case of pulse oximeter, its value is, let's say, suppose you are measuring and your value comes out to be 93%. And suppose you are trying to breathe in very nicely, very heavily, so that your oxygen level is increasing. It will take some time before it shows, let's say, 94% or 95%. Why? Because the output is not changing very fast. It is actually taking the average value and all. So the percentage change, it is slow in the case of a pulse oximeter. It does not show very fast. Okay, so that is what is basically a response time. And how much, like suppose if it is having some value 10.95, obviously for showing 10.95 it should go from 0 and change to 10.95 or 10.9. Or if you are going to take a analog scale, then the needle should go from here to here, and it takes certain time. So suppose if it has to reach here, how much time it takes to cover almost 95% of the distance, or how much time it takes for getting 95% closer to the original value, that time is taken as the response time. If you are in a very critical situation, the response time is very crucial. So if you want a faster response time, you will have to spend more. Next is repeatability. Repeatability means if suppose the value does not change, if suppose the temperature is 10.35 and you are measuring for the first time, okay, you get a value of, let's say, 10.32. Next time you measure, you get a value of 10.37. Another time you measure, you get a value of 10.33. Another time you measure, you get a value of 10.39. Like that it is changing. Sometimes next time you get 10.35. So you can see that the values are lying close by. So suppose if this is the value that you want to track, you are again and again taking the reading. So you might be thinking that, okay, this is accuracy. No, I am talking about repeatability, wherein you are trying to take the same measurements again and again, and the values are lying within a close range. So repeatability is how varied the different outputs are relative to each other. So how much they are varying, how much the reading is repeating itself. So if it's a very accurate system, it will keep on giving 10.35 reading itself, and it will be a very reliable system. It's also because its repeatability is very high. Okay. So the repeatability is something that should be targeted, but it is not very easy to get a a high repeatable system. Okay. Next is calibration. Calibration is when you use a sensor or when you use an instrument, after some time, due to the wear and tear, the accuracy of the sensor will go amiss. That means its accuracy will keep on changing. So in between you have to recalibrate it. That means you have to again calibrate it so that it is able to find out the correct value. So suppose, how do you recalibrate it? So there might be a certain small knobs or certain screws that you need to tighten the sensor, and that will recalibrate. So how do we generally recalibrate it? So you have to study recalibration a little bit in detail, but just to give you an example, suppose if you want to measure the weight of a 1 kilogram bar, okay, suppose you are using your scaling, a weigh scale in a gold shop, Okay, so it's very much required that it's supposed its measuring range is from 0 to 1 kilogram, so it can measure this much kilogram accurately. So you want to now, we are using the machine. If after some time the original weight, suppose if it is 65 grams and you are measuring and you are getting 63 grams, then the shopkeeper is at loss of 2 grams gold. So that should not happen. So generally what everyone does is, suppose they have uh, uh, a gold piece which is having a weight of, not gold, any other metal which is having a weight of, let's say 5 grams, then 10 grams, and let's say then 50 grams, 100 grams, like that. And after using the scale for some time, a calibrator will come, a person who calibrates the instrument, he will come and he will place this 5 grams and see if the reading is correct. He will place this 100 grams and see if this reading is correct. He will place 50 grams and see if the reading is correct. If the reading is not correct, he will make adjustments in the sensor to get the accurate reading, so that after his calibration process is over, you can again start using the weighing device for getting the weight of the gold. And this calibration process should be done for each and every instrument again and again and again. Generally in any labs you would go, they will have a definite time span within which they will try to do the calibration of the instrument, or calibration of the robotic system is also done at the industry level. So if you have installed an industry level robot somewhere, in regular intervals you will have to keep on recalibrating it so that its value is accurate, or it is giving you accurate values. Okay, but whenever you do the calibration, it should not take very long time, otherwise you are losing the work time of the robot. So the time and work required to accomplish the calibration process should be as minimum as possible, and at the same time the sensor should not require frequent recalibrations. So when you are trying to maintain these two things, obviously you will have to use very good materials or raw materials when you are making these devices or sensors. So obviously when you look at these things at the calibration, that it should not go for frequent calibration, and at the same time the calibration procedure should be very fast. For these things, again the price will go up. So what are the desirable features? These are the desirable features. That means what is expected? The expected is that you should have a high accuracy, high precision. So precision is again resolution based, okay. Wide operating range, that means the range of values, the lower and the maximum range should be high. Obviously that talks about the linearity also. The high speed of response, that is something that is desired, that the sensor should be having a good speed of response. Then it should be very easily calibrated. Minimum drift, that means it talks about the frequency of calibration. That means the accuracy is not changing very frequently, because once the accuracy changes you will have to do recalibration. So for the recalibration to not happen very frequently, you will require that the system should have minimum drift. That means it should not be very easily losing accuracy. Okay, the loss in accuracy should be very gradual in time. Then it should be highly reliable, means its value should be accurate, its value should be having high reliability, and also good sensitivity, okay, and its reading should be reliable. And the last is that it should cost as low as possible. This is something that is if you go for lower cost, you will have you will lose on these things. So you have to look at how much economical I can be, at the same time trying to keep all these aspects together. So with this, we will finish the selection and implementation of the sensor system. Thank you.